Hello, my name's Mark Massell. I'm an engineer with a physics background. I plan to go through the algebra and the matrix of managing neural networks. So this means designing a neural network, showing how the feed-forward works to give you a final result, and then deriving the backpropagation such that you can modify correct weights such that the neural network will learn. Now, there are many videos on YouTube showing how such a system works. There are also a few pretty good ones on matrix calculus and matrix notation, but I find that some of them use a lot of notation, indices, which are a bit confusing. So I just plan to go through the basics of the matrix manipulations, but I plan just to use the one indice, which is the layer of the neural net. Before we start, I just want to give you a few prerequisites, mathematical prerequisites, which you will need. I plan to talk about matrices in terms of row column, so I might use this notation that will show a matrix with a certain number of rows and a certain number of columns. Now, of course, you also need to know how to multiply matrices together. So if you have, for example, a 3 by 2, 3 rows, 2 column matrix, and you multiply that by, say, a 2 by 4 matrix, first of all, the matrices are only possible to multiply together provided the columns of the first matrices is equal to the number of rows in the second, so those numbers have to be the same, and then the final result will be a 3 by 4 matrix. So that's one thing. You also need to know what the transpose of a matrix is. Transpose is really when you have a matrix, for example A, B, C, D. The transpose of that, signified by the T there, is simply swapping the rows and columns. So the rows and columns swap, you would get A, B, C, D. Now, it's important to know this because sometimes you get into a state when you can't multiply matrices together unless you do this transpose. The next thing to know is a little bit about the partial derivative. If you have a function that's a function of two variables, say for example x squared plus y squared, if you want to differentiate that with respect to one variable and keep the other one constant, then the terminology is to use a differential like that. So d of that function, let's call it z, dz by dx will be 2x, and also dz by dy, keeping x constant, is 2y. So that's basic differentiation. The next thing you'd need to know is the chain rule for differentiation. If you have a z, which is a function of y, for example, and then y is also a function of x, then y and z are dependent variables. And so how would you differentiate z? Well, you would do it by the chain rule, which says that dz by dx is going to be dz by dy times dy by dx. So this is the chain rule, which we're going to be using quite a lot because with the backpropagation we're going to be working out what the error is at the end of the neural network and then back propagating that through to the beginning again to find out how to adjust the weights. So these are the basic prerequisites. Just one more thing to say actually. If you have a function such as this, j equals t minus y squared. This is really just a chain rule problem again if you want to do the differential of dj by say dw. But I might refer to this as the outside, so dj by dy being the outside, that's dj by dy, and then dy by dw as being the inside. So that simply becomes the outside goes to 2t minus y, and then the inside taking the negative outside, and it's dy by dw. Right, so I've pre-drawn the neural network example that I plan to use, and I'll go through it now. So we have input neurons, 2 input neurons in this example, with data x. Now there's no summation or no function going on here. That x is just multiplied by a weight. And I'm just going to show the top neurons here. As I said, I'm not going to mention any indices because they'll just naturally flow out of the matrix calculations. I'm also showing for layer 2 there's 3 neurons here, as you can see. The inputs are the sums of what's coming in from the previous layer, including a bias term. The bias term is labelled with a 1 here to show that it's actually in layer 1. We then have 2 neurons in layer 3, similarly with a summation here, and then going through the activation function, which could be a sigmoid or a rectilinear type function or something similar to that, and then output to the next layer, which layer 4 here is my output. So I'm showing 4 output neurons. I think it's important to show that the matrix calculations are quite happy with multiple outputs, and the output is y. So I'll show you the typical process to go through the feed-forward network, and then we'll go and look at a cost function, which will be basically how accurate the neural network is at predicting what the result should be, and any errors we will then figure out what is to blame for the errors, as it were, which weights are to blame, and figure out from that what to do about it. I've missed out the weights 3 here, and the activation 3 here, which is the result of the activation function. Okay. Just a note here about the dimensionality of the matrices. What we'll see is that if we've got 2 input neurons here, then the dimension of this matrix is an S by 2. S being the number of samples, just for one sample, obviously that's 1. 2 neurons, so that's a matrix of 1 or S rows and 2 columns. Then we have to manage the weights here, and we will have a matrix of size, the number of neurons in the first layer as rows, so 2, and the number of neurons in the second layer, so 3. We will then have a solution to this, which will be an S by 3. We will then add the bias, and again that will produce an S by 3 matrix. That will then go through the activation function and produce another S by 3 matrix, and that will then be the next matrix to come up and feed into the next level, where it will then multiply by, this time, a matrix of 3 rows by 2 columns, and so it will progress. So let me just show you that in a little bit more clarity. So the input side, we will have a matrix here, as I said, of S by 2. So this will be our data coming in. Let's just move that out of the way first of all. Then the weights get multiplied, and as you can see here, it's the number of neurons in the first layer by the number of neurons in the second layer. So they get multiplied, and they give you a result here, which is related to the size coming down in rows and 3 neurons representing layer 2. And then we will add biases onto that, another S by 3, and finally we get, after going through the activation function, we get the answer as an S by N2 matrix. Right, let's have a look at the cost function now. So when you finally get to an output here, Y matrix, the output matrix, what you'll have, based on various training inputs, you'll have the neural network's first attempt at trying to figure out what the answer is, based initially on random weights. So first of all, we need to know how accurate that is. So there's an error. The simple error really is what the true value should be minus what the actual neural network output is. Now the cost function is defined as J equals, or one particular cost function is t minus y squared, and the sum of that typically over the number of data in your data set, how big the data set is. There are various different types of cost function. There's lots of information around as to which is the best one to use, but this one has its roots in the Gaussian function, and so is generally reasonably good. Maybe not so good for outlier data, but anyway, let's use that one. So that's our cost function, but in fact what we're going to use is a slightly modified version. We're going to use the sum of a half true value minus the output of the neural network squared. So this is our cost function. The reason we use this one is that when we differentiate, we get rid of this, and the maths looks nice and neat. So let's have a look at backpropagation now. So what is backpropagation first of all? Well, we know we've got our output here and we've defined the cost function. So our aim is really to send data through the neural network such that by adjusting the various weights we can minimize that cost function such that then the output of the neural network Y will be the same as the true value that we expect. So how do we do that? Well, we look at our cost function J and we see what is most responsible for that. For example, this weight here. Of course, what we could do is we could just adjust all the weights at random until we get the desired output, but for large neural networks that would often take longer than the present age of the universe to do, so clearly we can't do that. So we have to figure out a much more sensible way of adjusting these weights, and the way to do it is to look at the cost function and see what responsibility each weight has to it, and then adjust that weight such that the cost function goes down. So let's look at W3 first, the weights of layer 3. And so what we need to do is we need to find out the rate of change of J with respect to W3. So that is dJ by dW3. If we write that down, that's what we need to find, dJ by dW3. And we know that our cost function here, which is this, t minus y squared dw3. So let's differentiate that. We're not going to worry about this summation sign here. That sums across all the samples, so we'll figure out that that will actually be managed by the matrix calculus. The matrix calculations will automatically do that for us. So how to differentiate this? You differentiate the outside and then multiply it by the inside, so that 2 comes down to get rid of that one there, t minus y, and then the inside y, so we get minus here, and then dy by dw3. So that's tidied things up a little bit. Now we have to figure out what to do with dy by dw3. And if we have a look here, so if we look here, dy by dw3 here is simply, in the way there's a z4 which is a dependent variable. So what we're going to do is we're going to use a chain rule here. So we're going to say that that equals this, and we're going to split this up, so dy by dw3 gets split and our dependent variable goes in here, and that is dz4. Now, what is dy by dz4? Dy by dz4, how that's going to change is based on the activation function here. So what we need to do here is differentiate the activation function. So we'll just label that as f prime z4, and then we've still got a dz4 by dw3 to worry about. So let's have a look at this dz by dw3. What we can see here, it's the rate of change of z4 by w3 here, and so if we were to plot that, z4 w3 here, what you'd see is the gradient here is actually the activation A3. So we can replace this here by A3. So we end up with an equation minus t minus y, differential of our activation function, times A3. Right. And what we can say here is that this, we'll label this complete function here as del 4. So what we have here now is we have dj dw3 is equal to del 4 A3, but we're not quite done yet. If we look at the dimensionality of this, minus t minus y is a s by 3 size, f prime z4 is also an s by 3, but A3 here is an s by 2. So if we're going to multiply these together, we're going to have an s by 3 and an s by 2. So clearly this isn't going to work here because the matrices are not going to be multipliable. So what we need to do is do a transpose and flip this s by 2 into a 2 by s here, and then multiply it by an s by 3, and then as you can see here we can multiply them together and we end up with a 2 by 3 matrix. Right, so the final answer here is that dj by dw3 equals A3 transpose times del 4. Okay, so how about the bias term? So dj by db3, we can write that dj by db3 equals the sum half t minus y squared by db3, which equals, by using the chain rule, this time dj dy by db3, and so dj by dy is effectively the outside bit, which then if you drop the summation sign, that becomes t minus y, and that leaves dy by db3. So that's the inside bit, so we have negative sign comes out the front, and we have a dy by db3. Now the dy by db3, we also need to use the chain rule, because our independent variable here is z4 like last time, so that equals minus t minus y dy db3, dz4 is the dependent variable, dz4. Now we know that dy by dz4 is simply the activation function, or the derivative of it there, and as far as dz4 by db3 is concerned, here we can look at that as being b3 and z4 here, and the gradient here is simply 1. We're looking at dz4 by db3 here, so the bias is actually just a weight, and the actual bias really is just 1. So the gradient is 1 here. So that means what we end up with is that dj by db3 is simply the del 4 function. If you recall this function here, we're calling the del 4. So let's just summarize where we've got to. For our first calculations, we have that dj by dw3 equals our activation transposed times del 4. So that's our first one. And dj by db3 equals del 4, where del, of course, del 4 equals minus t minus y, differential of our activation function. So that's where we are at the moment, and the next stage then is to go one step further back, and so we're going to find out the effect of W2 on that cost function. And as you can see, we have to then use a chain rule to get back here, and we've got another couple of dependent variables here to handle, and we'll see how to do that next. So now we need to calculate dj by dw2, which as before, the cost function is t minus y squared, but dj by dw2 Again, ignoring the summation, we end up with this dy by dw2, and this we can use the chain rule again, and that becomes dz4 dz4, and as we saw last time, this is just the activation function. You can see here y z4 dependent variable is that function, so we need to differentiate it, so that that we just denoted as this. So we end up with minus t minus y, differentiated activation function, but now we have dz4 by dw2. So again, we need to use the chain rule on this. We can again note that this is just del4, so that simplifies things. And what do we do with this dz4 by dw2? Well, if we have a look here, we've got quite a long way to go to w2, so the next non-weight result of calculation is an a3 here, so we have to do the chain rule with a3 as a dependent variable, so that simply becomes dz4 dw2 dA3. Now we have to figure out what dz4 by A3 is here, and again it's like peeling back the onion. Each time we peel back we get a solution on this side, on this one we have to carry on with the chain rule. So dz4 by A3, if we have a look here, if we have this as A3 here and Z4 here, we see that the gradient here between Z4 and A3 is just our weight 3. So this is just our weight 3 matrix times dA3 by dW2. So coming back to here, that becomes del 4 W3 dA3 by dW2, and again we have this transpose problem, so we need to put this matrix in front of the del 4, so we end up with W3 transpose del 4 dA3 by dW2. Right, so let's just summarize where we got to. We got that dJ by dW2 is equal to W3 transposed del 4 dA3 by dW2. So peeling back that onion again, what have we got here? dA3 by dW2, dA3 by dW2. So what we need to do is to use Z3 as the dependent variable now. So this becomes W3 transpose del 4 dA3 dW2 by dz3, dz3. So what have we got here then? We've got dA3 by dz3, dA3 by dz3, and you can see that we just have the dependent variable as the activation function, so that becomes the function of z3 now, the differential, times dz3 by dw2. So let's have a look at that. dz3 by dw2, dz3 by dw2. If we look at that, we can consider that as w2 along here and z3 at the top. And what's the gradient here? If we look here, dz3 by dw2, the gradient is simply the activation of our layer 2 neurons. So this can all be rewritten as w3 transpose del 4 function of z3 and our activation A2. And we'll label all this now as del 3. And so we're nearly there. We have that this dj by dw2 equals del 3 A2. And as before, we've got a problem with the dimensionality here, so we just need to transpose. So the final result here is that dj by dw2 equals A2 transposed del 3. And in a similar way as before, let's not forget the weights here. So this is weight B2. So dj by dB2 now is simply del 3, where we've defined del 3 to be this as a function of del 4. So that's that layer, and all we have to do next is to carry on this procedure to get the contribution of W1 weights as well as a B1 bias. So let's proceed on. Okay, so our third step now. If we go back to our neural network here, let's find what effect on J contributes from W1. So we do dj by dw1 now. dj by dw1. The cost function again. By dw1. And that equals minus t minus y dy by, sorry, dw1 now, dw1. So, first step last time, z4, carry on exactly the same as before. dz4, no, sorry, dw1, dz4, dz4, and as we said, dy by dz4, the differential of the activation function, equals minus t minus y function z4, but now we end up with a dz4 by dw1. Right, let's just move that up a bit. And so, let's have a look at this. Minus t minus y, function z4. Now dz4 by dw1, again, what we have here, z4w1, we've got the a3 activation function there as a dependent variable. So dz4 by dw1 dA3 dA3. Now dz4 by dA3 as before, you can consider this as A3 and Z4, and the gradient here is weight 3. So just as last time, this becomes W3, and so we have minus t minus y function z4 w3 dA3 by dw1, and we'll transpose this like we did before, put it in front, and this del 4, so we end up with W3 transpose del 4 dA3 by dw1. So let's have a look. dA3 by dw1, the next one back is Z3 now, so we can split this up as dA3 dw1 dz3 now, dz3. So let's have a look. dz3 dA3 by dz3 is that function again, so that equals function z3 this time, and we're left with a dz3 by dw1. And as before, we can say all of this is now del 3. So we have that dj dw1 now comes down to del 3 dz3 by dw1. So dz3, so the next one back is A2, so that can be split up as del 3 dz3 dw1 dA2 dA2. So dz3 by dA2, we have a look here, dz3 by dA2, that can be looked at like this, and the gradient here now is W2. So this can all be written as del 3 W2 dA2 dW1. So the next one back here, let's have a look. We've got a dA2 by dW1, dA2 by dW1. Next one back here is Z2, so we can again use a chain rule, and we get del3 W2 dA2 dW1 dZ2 dZ2. Now then, let's have a look. dA2 by dZ2, dA2 by dZ2, it's that function again. So that comes to function of Z2 now, differential, and we're left with a dZ2 by dW1. So let's just move this W2 the other side of the del and do the transpose as before. So now we have W2 transpose del3 function Z2 dZ2 by dW1, and we can define this now as our del2. So the last thing to look at is what is dZ2 by dW1, and it's really just x. So if you looked at this as W1 and Z2 here, it's just the input x as the gradient here. So we're almost done. So we end up here as having dJ by dW1 equal to del2 times times x. But again, we have to move this x over here. We have to transpose, so that becomes x transpose del2. So that's our equation, and again, as before, the bias is fairly straightforward. It's just the del2 part, and this then gives us our other last two equations for the W1 weights. There. Okay, so let me just summarize all the equations that we've derived. Here they are: the dJ dWs, the dJ dBs, and the dels. I'd like to make a couple of important points here. I didn't explain in detail here, but between these matrices here, it's important to use the Hadamard product instead of the standard matrix multiplication. The Hadamard product is basically an element-wise multiplication like this. It's not a dot product. The second thing that I'd like to note is that when I said that the summation here was taken care of by the matrix manipulation, that's true for the weights, but for the biases you'll have to do a matrix column summation. So what you'll need to do is you'll have to sum the contribution from all the samples, so that means summing the columns of the matrix to get a final del that can be used as the dJ dB, which can then go to modify the biases. Furthermore, I'm going to show you an application where this actually shows that all these equations are working fine. I use this form where I divide by the number of samples in the data set. That can be achieved by simply dividing the dels by n. and in that way you don't have a problem when you implement the same solution for the biases. So let's have a look at the equations in operation. Okay, since the proof of the pudding is in the eating, I wanted to just show you the theory that really does work by I've written a little Visual Basic program here, a neural net application. I've selected an XOR and an OR dataset. So I've created this dataset by having two inputs. So these are the result of random number generator between 0 and 1. So when the number is below 0.5, I'm assuming it's a logic 0, and when it's above 0.5, I'm assuming it's a logic 1. And then I've created the XOR and OR functions. This is a 500-point data set. So the matrices we were talking about before, one matrix will be used for this complete data set as an input. The only other thing to mention is I've also got some input data conditioning going on here. So because we've got digital outputs, this filter will push anything that's below 0.5 closer to 0 and push anything that's above 0.5 closer to 1. It's really a very sharp sigmoid type function. So the architecture for this sort of application, I think just one hidden neuron, just one hidden layer, 5 neurons should be adequate. And we can later on modify this, prune this to make sure that the data set algorithm is really being learned rather than the data itself. So training, I can set this off soon, but I just wanted to show you that I've also added a learning rate here. This is a number that multiplies the dj by dw's before they get applied to modifying weights. A larger number obviously means more of the dj dw gets used and the learning rate is higher. Smaller number learns lower learning rate but can produce more accurate results. I've also added a momentum. This is where dj dw from the previous iteration gets applied to the current weights. So it's like a momentum that helps the system, helps force the system down into the further lower in the error plane. Right, so let's get it going. It should start it. Obviously starts with a pretty high error and soon goes down. As I said, depends on the learning rate. I can show you that if I put a higher learning rate, that will now go down at a higher rate. Not so obvious there. Let's zoom in on it. Let's put a lower learning rate in. Now let's put a higher learning rate in. You immediately see that it's learning much quicker. The error is going down faster, but that won't give such good results. Let me put it back to 0.1. We see it's gone down to 8% already. It will quite happily go down to below 0.5% given enough time. Let me just go back to the architecture here, and we can see here that I'm also indicating with a different brightness color level here the neurons that's more active than the other neurons, and so this can be useful in pruning the system. In fact, for this application I've run this with just one hidden layer but only 2 neurons, and it performs quite well. So that's really about it. Let me just show you the system here now that it's gone down to much more reasonable 2.8%. I just wanted to show you the architecture here, and this sort of really hints at the fact that this algorithm could learn quite happily with just 2 neurons. Just to say also that I've got a function here that switches the biases on and off. I've found that the training is a lot faster with the biases on rather than off. So even with a soft plus activation function here, it really does aid the learning rate to have biases in the system. Okay, thanks very much.